In this video, we are going to consider our first research question on page 6 of our notes. And the research question has to do with Force City's goal to develop a regression model to predict the appropriate selling price for a home using certain measurable what? Characteristics collected on the independent variables we mentioned in the earlier video. So the first attempt at developing the model will be to run a multiple regression computer program using all available independent variables. So let's look back at the data set in StatCrunch. So let me close out of this and you see that I have list price. We want to see if it can be explained by the square feet of the home, the age, the bedrooms, the bathrooms, and the garage number, the number of garages that the home has. So to see how to fit a multiple linear regression model, we'll go to statistics, go to regression, and then multiple linear. Click on multiple linear. What variable do we want to explain? That is the price. How did we get to that price? That's what we'd like to explain. So choose list price for Y. And we want to see how that can be explained by the square feet, age, bedrooms, bathrooms, and garage number. So those will go under X variable, square feet. I'm going to hold down the control key on age, bedrooms, bathrooms. I'm going to drag this down a little bit and then garage number. And the next thing I like to do is to compute. And that will go really fast and give me the multiple linear regression model. So I've copied these results onto our notes. And we can see here the list price and the independent variables are, of course, square feet, age, bedrooms, bathrooms, garage number, and the fitted model or the prediction model. This is our prediction or estimation model. And this tells us that list price is related to each of these variables in this linear regression model. Well, what can we use this model to do? That takes us to the model derivative. For instance, if we are supposed to use past data to make a prediction of the future, for instance, to estimate or predict the value of a residential property with the following characteristics, where the square foot is 2100 square feet, age of the house is 15, number of bedrooms is 4, number of bathrooms is 3, size of the garage is 2 garages. Well, all we need to do is to substitute each of these values. So I'm going to substitute 2100 in here, age right here, bedrooms, bathrooms, and the number of garages right here. And if we do that, we end up with a predicted or list price for a residential property with all of these characteristics. And that will lead us to this equation, which would give us a final approximate answer of $179,730.33 approximately. This is the first derivative of fitting a linear model based on past data and use it to make a prediction of the future. Okay, something very important for us to note is that you see, for this prediction equation or model, each of the independent variables has what? A coefficient. So for square feet, the coefficient is this value. For age, you have negative 114.4367. For bedrooms, you have negative, and also bathrooms, you have positive, and for garage number, we have positive. Why am I calling your attention to this? Um, we expect that as the square feet of a home increases, the list price should also increase. So it makes sense that the coefficient should be positive. We expect that sometimes as the home ages, that it's what? Its relationship with what? The list price could be negative. That is, the list price might fall. Then bedrooms, number of bedrooms, negative. Let's see what we saw earlier when we looked at list price versus bedrooms. This is supposed to be what? Positive. Why is that the case? I want you to keep this in mind because later we'll find ways to address this. This might be telling us that our model is not the best model. And so there might be room for improving the model. Okay? Now that begins to throw a little bit of what? A little bit of concern regarding the validity of this model. And that leads us to ask questions like, each of these what coefficients, are they really, really significant? Are they something to reckon with? Or are they dismissible? In statistics, we are interested in if each of these what coefficients, if they are significant, if they are practically what meaningful or usable. So that leads us to three important questions, and that is hypothesis test for testing that any of these slope parameters is zero. If it is zero, it simply means if, for instance, the slope parameter for bedrooms, if it is really close to zero, it might be an indicator that bedrooms is not really in combination with other what independent variables, a very useful predictor to include in this model. And so we might need to drop it. We'll soon see more of that. We might also be able to carry on a hypothesis test for testing that all of the slopes simultaneously are all equal to zero, or perhaps test if just a subset of the slopes of pertaining to each of these independent variables are not all zero or zero. Let's consider an example of how to do this. So, um, if we have another research question, which is which, if any, of these predictors, square feet, age, number of what, bathrooms and bedrooms, which of them is really, really trying to help us explain some of the variation in list price? That means we would like to conduct a hypothesis test for individually testing whether each slope parameter could be zero. One of the ways we can do that is to look at each of the independent variables and their respective what? P-values. If we set a significance what? A significance level of, let's say, 0.01. The p-value in this case is lesser than what? The significance level. So that means that we're going to reject the hypothesis that the coefficient, that the regression slope for this guy is equal to zero. And we're going to go in favor of the fact that it is statistically what? Significant. And that is because our p-value is lesser than the significance level, which means square feet seems to say yes, it is what? Useful in explaining the dependent variable, which is list price. The same argument can be made for each of these what? P-values, because they are all lesser than the chosen significance level, and so they are all statistically significant. Okay, so as it stands, in this case, we are looking at what we saw earlier in the model. When we looked at the regression model, we had each of the coefficients, the regression slope coefficients, and we're testing hypotheses on each of them. Okay, and with that said, let's go back to what we're working on here. So what do we learn from this output? If the research question is the model containing all the included predictors more useful in predicting the list price than the scenario where we don't consider any of the measurements collected on the explanatory variable? The answer to that question is nested in an hypothesis test. We're going to test hypothesis regarding all of the what? all of the regression slopes all at once versus that at least one of them is not zero. If at least one of them is not zero means not zero relevance. So to do that, we need this p-value from the ANOVA table for the regression model. And the p-value here is so small that it is smaller than 0.001. So if it is smaller than 0.001, which is also smaller than what, 1% level of significance, it means that we are what, going to reject the null hypothesis, which says that all of them are all what, zero or zero relevance. And if we are rejecting that, that means we are going in favor of the alternative that at least one of the regression slopes is not zero, aka at least one of this what? One of these variables or independent variables is useful in predicting the least price. What if we don't want to test all of them at once? What if we just want to test one individual explanatory variable to see if it is statistically significant in explaining the least price response variable? For instance, if I'm interested in just looking at if the least price is related to ohm square feet after taking into account all other what? Explanatory variables included in the model, well, in this case, the null hypothesis would be I'm taking home size, which is measured in square feet, as the first what, independent variable. So that would be testing that beta 1 equals to 0 versus the alternative that beta 1 is not equal to 0 or possibly greater than 0. Okay, in this case, I would go back and I'll look at the p-value for square footage, square foot feet, and in which case you have what, 0.0001. So the p-value is 0.0001, which is lesser than 0.01, which means again we reject the null hypothesis in favor of the alternative. A similar argument can be made for number of bathrooms. We want to see if the number of bathrooms is related to, excuse me, this should be least price, taking into account all other independent variables. This time for number of bathrooms, I see this as the first independent variable, second, third, so this is the third independent variable, and then the fourth is bathrooms. So in this case, I am testing the null hypothesis that beta 4 is 0 versus the alternative that beta 4 is not 0. What is the p-value corresponding to bathrooms? Let's go back to the output. That is 0.0266. So that is 0.0266. Okay. Looking at this, we can see that this is greater than what? Our alpha, if chosen to be 1% level of significance. So this time, we do not reject the null hypothesis. If we do not reject the null hypothesis, which is claiming that the relevance of what? Bathrooms to pricing what? Homes is 0. Well, that is independent. That is kind of telling you or that in this case, at 1% level of significance, bathrooms is not very useful in predicting what least price. Could we have seen that coming? Sometimes. Let's go back to the fitted model. Okay, and you recall that from the fitted model, we have a negative what? Coefficient here for negative coefficient for bedrooms, and for bathrooms we have positive. That seems good. Bedrooms seems very, very suspect, and we might be coming back to that. Okay, so this might be telling us that including bathrooms in this model, not necessarily. When it comes to model fitting, one thing is very, very important. It is that there is no one single model that is perfectly a perfect fit across board all the times. According to a very, very popular saying, All models are wrong, but some are useful. So we have emphasized there, or we have established there, that the square footage of a home is very useful for predicting the list price. So how much of an effect is that square feet having on the list price while taking into account all other predictors included in the model? So in this case, we'll need to look at constructing a 95% or a 99% confidence interval for the what? The estimate of that effect. And we can see that it ranges from 55 to 70. This does not, this does not include what? Zero. And because it does not include zero, it means that the effect cannot be zero. If the effect cannot be zero, it's another way of saying the effect cannot be nothing. The effect is something or statistically significant. So this range here, the confidence interval for the estimate of the effect of the square feet on the list price, is very useful in this case. Okay, so that answers that question. And how do we output these pieces? If you go back to StatCrunch, you will notice that by default it does not output it. But if we go back to edit and we scroll down here and we choose the 95% confidence interval for the what? For the mean response, we'll be able to get each of these values here. So let's see. We have quite a number of them here. Take note, it's not for the individual prediction. Let's see, that will give us this guy, and let's compute. Oh, that gives us the confidence interval there. Sorry, let's take that again. Okay, so we have those pieces there.